Good morning, everybody.
Good morning.
Oh, yeah. Nothing like 200 geeks awake at 9 in the morning. What a sight. So this talk can be one sentence. In every round, every node picks a random target, exchanges some information, and waits for the next round. This is what I like about gossip algorithms. They're simple. They're really literally one line. Because they're so simple, they're robust to implement and simple. And yet they're remarkably efficient and fault tolerant. Understanding the basics of them will actually give some insight as to when they work and also why and when they don't work, why they don't work. So today I'm going to talk about 3 protocols of this family and go down to the basics, and we'll go right away. So the story actually begins with the company that introduced and commercialized this technology. How many people recognize the technology in the company? Not a single one. Okay, this is the company that also introduced the first PC, the first object-oriented programming languages, the mouse, the first graphic display, the Ethernet, the first laser printer. How many people know what I'm talking about now? All right. So this is Xerox. It took it 20 years to take this first successful paper-to-paper copy. This was the first successful copy of one paper to another. It took it 20 years to commercialize this and become a commercial product. And then they realized that the office of tomorrow is going to be at least partially digital. So they founded Xerox PARC, and they recruited this amazing group of researchers to help bring Xerox to the digital age. And this is where this amazing group of scientists encountered the problem that led to the birth of these gossip-based protocols. So what was the problem that they were grappling with? So in the grapevine system, which was also one of the first, if not the first, distributed networked system, they needed to keep copies of data consistent, and they came up with this randomized protocol for doing this, which later received rigorous analysis, first in a PODC 87 paper, and then even further, more strict, and some variations of analysis in a wonderful Fox 2000 paper. So what are we talking about? So the problem, the basic problem in Grapevine was initially to keep copies of mail synchronized throughout a cluster. So mail would arrive at one of the nodes, and from here on, I'm going to talk about a network of nodes and refer to all the players or participants or processes or PCs simply as nodes. So mail arrives at one of the nodes, and the obvious first strawman solution that they came up with was direct mail. As soon as the mail arrives, the node multicasts the mail to all of the nodes in the network such that users can access their mail from any node in this network. Problem? First of all, multicast is somewhat expensive. Networks did not necessarily support it, so the node had to contact one at a time each one of the nodes in the network, which was already getting very, very scalable at a time. We're talking about 8 to 16 nodes. That was a heavy burden. And it was difficult because there were also failures. At the time when the mail arrived and the node was trying to contact one of the nodes, it may be down, or there may be message omissions, so it had to remember to contact later, and then maybe when later the node that used to be down is up, now the origin would then fail. And so they've run into a lot of difficulties of keeping this direct mail method working. So their second attempt was what they called anti-entropy. So anti-entropy worked by occasionally having nodes contact one another and compare their database of mails, and later they used the same thing for something like DNS, for a network addresses directory. So they would just compare their entire database and see what's missing, and then send each other the missing information. So that actually worked and converged, and any information in the network would eventually reach everybody. So already there was some randomization here. So by occasionally picking a random communication partner every period of time and synchronizing with them, there was already this phenomenon that over time, all necessary information got everywhere. But it also fundamentally relied on synchronizing databases, comparing them, and sending what's missing, keeping information essentially forever. Even deletions had to be kept around for quite a long time in order for the synchronization to work. So it really didn't rely on randomization to spread this information. Randomization was just the communication protocol. It was quite expensive and quite slow to operate. So finally, this led to the first actual gossip protocol, which from here on I will refer to as randomized gossip. And that was the rumor mongering protocol. So here the idea is to totally rely on gossip to spread information. So mail or any kind of update, more generally, arrives at a node. The node keeps it for a certain duration. During this duration, every once in a while, every period, it wakes up, sends a copy to a random partner, and then after a certain duration, if you believe that the gossip worked, it marks this information as no longer hot and stops gossiping about it. All other nodes do the same thing. Every once in a while, wake up, send a copy of their information, do that for a few rounds, exactly the duration that the gossip predicts that's needed, and then mark this information as, okay, completely synchronized, gossip has completed, and stop gossiping about it. So complete reliance on the gossip protocol to disseminate the information throughout the network completely and reliably. So now let's move away from Grapevine and look at this more foundationally. I know it's early in the morning, but my hope is to look at the foundations, look at the analysis of this without scaring you, and to actually make it more accessible, not less. Let's see if I succeed. If I can understand it, I think anybody can. So in order to do this, we do need to look at actually, the precise definitions and assumptions made in this algorithm. It's a really simple one. It's a one-line algorithm. So all we need is to say the following. We assume that we ask the protocol to work in logically synchronous rounds. So they're logically, it's not really instantaneous as in real-time instantaneous, but we're not going to mix and match messages or steps from different rounds. So logically, all the nodes in the network go through rounds one at a time where they do their operations, process, and continue to the next round. So logically, it's a wave of actions, local and communication, one by one. So that's what we mean when we say synchronous rounds. And we're going to implement it this way, and we also need this for the analysis. As we said, the algorithm is just one line. In each one of these rounds, a node picks a random target and exchanges information with it. For this to actually be meaningful, for this to be well-defined, implicitly we assume that every node knows all the other nodes in the network. And from here on, we're going to use n to denote the obligatory number of nodes in the network. But implicitly notice that the assumption here is that there's full information and full connectivity in this network. So every node can pick another node perfectly uniformly at random. This will not work if there's any kind of skew or information is lacking, and this assumption does not hold. And the assumption about the network is that every node can, in fact, form an interaction with every other node in the network, say like a TCP/IP network. So in this framework, there are many, many protocols and many variants. I'm going to look at 3 today. The first one is the analysis of this rumor mongering that I just talked about. Just a simple dissemination of information that replaces multicast. And this was the protocol and the system that was developed at Xerox PARC. The second one will be the use of gossip techniques for failure detection. And these were methods developed at Cornell University in order to scale failure detection. And the third one will be network discovery, where the information we send is used to build the network itself. And this is a method and work that was developed by the Akamai engineers when they faced scalable networking. Okay, so let me start with the simple information dissemination, rumor mongering. So we'll do that first by demonstration. So here we have a network. It's a full network. Everybody is connected to everybody else. We will call the node that first holds a copy of the message informed. In the literature, sometimes it's infected or many other terms. Here I will call every node that holds a copy of the information that we want to spread informed. All right, so we have the first node, which is informed, and it wants to spread the message using randomized gossip. What it's going to do? Okay, so first let me, for clarity of the slides, get rid of the network, and we're going to assume this implicitly from now on. It's going to pick a random partner and send information to it. So here I want to give a point of view which you won't actually find in the literature, and it's also not really precise or correct, but just my intuition, the way I think about it. So the way I think about it is the original node had the responsibility to send a copy of the original gossip message to N recipients. It's going to recruit help from the first partner that it talks to and says, look, why don't you be responsible for half of it, and I'll still be responsible for half of it. Okay, so in the next round, and so now we have another node which is informed, and in the next round, they're both going to proceed autonomously and concurrently. So now two nodes are actually gossiping, and they're doing the same thing. They're each picking another node to help them, not just to inform them, but also to become active gossipers of the message. Okay, so it's as if they say in the next round, okay, we had responsibility each for half of the dissemination, and now each one of us is going to choose a partner and ask for help in a quarter. So now we have 4 nodes, each one of them responsible for further spreading the message to a quarter. And this continues in the next rounds. It's n over 8. Now, I only have 8 nodes on this slide. So in principle, we should have completed if this was precise. But we know that actually what happens is that there's certain inefficiency. Nodes will collide and send the same information to the same target. So actually, we didn't finish, and another round is needed in this example to finish. Let me actually scroll back and look at the process again a little bit slowly. So what really happens is that first, most of the nodes that are chosen as gossip partners are not informed. So with very good efficiency, every gossip message reaches an uninformed node and turns it into informed. And this happens so long as about half of the network is still uninformed. We have the probability of at least a half of reaching an uninformed node. So really, every round is very effective. It grows the number of informed nodes by a constant factor, almost doubles the number of informed nodes. At some point, the network starts becoming mostly informed, and here we start wasting communication just to reach the few unlucky nodes that are still uninformed. So here there's only one uninformed node, and everybody is trying to target it. Hopefully, within a few rounds, somebody will actually pick this unlucky node and complete the process. So this intuition is, in fact, what we can use for formal analysis. So to look at the formal analysis, we're looking at a number of aspects of the process. So first of all, again, we have n nodes, and we're going to look at the gossip process and its complexity, focusing on gossip of one message only. There may be a lot of messages, and in fact, in most systems, there may be multiple messages simultaneously being gossiped, and we're going to piggyback on the same connections and potentially transfer many messages. But for the analysis, it's enough to follow what's happening for one message only. And then it turns out that the basic framework that I gave, still, there's a lot of flexibility. So the framework says in every round, a node picks a random partner for interaction. But doesn't really say then how do they exchange information. And in fact, it turns out that very different behavior occurs if the information is pushed to the partner, if the information is pulled from it, or if it's pushed and pulled. And I think that understanding it gives a lot of insight on these processes. And I'm going to do it in the next few minutes. It's going to be a little bit of math. If you really, really dread it, this is the time to go on your Twitter and come back in about 20 minutes. So in about 10 minutes, I'll go back to failure detection. Or if you were really waiting for it, this is the 10 minutes where you can take a little bit of math, but really a little bit. I mean, it's not complicated at all. By now, there's very, very clear intuition on how this process works. And I'll try to be precise and at the same time gloss over some details. So let's first look and say something obvious. It's sort of obvious that if at every round, every node is allowed only one interaction, one connection with one other node, the best we could do is spread the message in log n number of rounds. Why? Let's just look at the graph of all the connections which are formed during this process. Okay, this is a graph where each node has out degree, has a logarithmic log n number of connections that it chooses to other nodes. And it's well known in the theory of random graphs that this graph will have log n diameter with high probability in expectation and also with very high probability. So if the graph has log n diameter, and we're starting with a message on one node, it will take log n steps for that message, even under the best schedule, the best algorithm, to cross the graph. If you're looking at what I'm saying and the slide, it's not the same. This is saying the same thing, but actually proving it. But if you just think of this as a random graph with log n edges, you immediately see that it will take logarithmic number of steps for the message to move from one end of the graph to another. Okay, now let's look. So this was the lower bound. So there's nothing you can do better with so few connections. Now let's look at actually an upper bound. So how long does it take to actually complete? And we're going to split the analysis into push and pull. We'll start with the push analysis. And we're going to split the push analysis into two parts. The first part is when less than half of the network is informed. So the message has reached less than half of the network. Well, what we can say then is that every push by an informed node has a pretty good chance of succeeding, at least half. And in expectation, altogether, the set of informed nodes have an expected half, is expected to grow by a factor of at least half of them. So at least half of them actually get to uninformed nodes. So this is an expectation. There are two things that we need to do in order to move this into a high probability, high assurance result. And in this talk and in most other papers, we will consider something that happens with probability at least 1 minus 1 over n. So something bad, something doesn't happen with probability 1 over n. We'll consider that small enough probability. It's very easy to get this to 1 over n squared or any probability that you want, any polynomial probability that you want. So in order to move from this expected behavior to high probability behavior, we need to consider two things. One is that even if an informed nodes get to an uninformed node, there still may be collisions. So there's some loss of efficiency there. And secondly, even though the selection of partners is completely independent, the actual sum of uninformed nodes that become informed, that's not an independent sum. But the dependence is small enough. Every two nodes can affect each other by at most 1 if they collide. And the collisions are rare enough that you can rigorously show that the actual progress of the process is very close to the expectation. So our intuition and actual rigorous analysis are completely perfectly aligned in this case. Until half of the, or any constant fraction of the network are informed, every round increases the set of informed nodes by a constant factor. It's not exactly doubles, but it's close to it. I can definitely say that it at least grows by a third. So this is the first half of the process. The second half of the process is when already a significant fraction of the network, let's say a half, are informed. What happens then? So this is the part where we're losing a lot of inefficiency just to get to the last remaining nodes. And those of you who are familiar with coupon collector analysis, this is exactly what's going on. We're going to throw a lot of messages, n log n messages, just to make sure that every single node is not missed. And so now, in each round, at least half of the network is informed. So in each round, we are, in fact, throwing a linear number of messages, n over 2 at least. And so if we looked at the probability of an uninformed node to actually receive any one of these messages, there's a little formula there. It's really a trivial formula. If I'm an uninformed node, the probability that somebody, one other node chooses me is pretty small. It's 1 over n. The probability that I'm not chosen by that one other player is 1 minus 1 over n. But the probability that all of the informed nodes, at least n over 2 of them, all of them don't choose me, that's 1 minus 1 over n raised to the power of the number of informed nodes, at least n over 2. And if you look at this, this formula converges very, very quickly to e to the minus half. And so with constant probability, the actual number doesn't really matter whether it's a third or 1 over square root of 3. It's a constant number, non-negligible one, that if I'm uninformed in a round where n over 2 messages, random messages are sent, I will receive it. So that's the probability. In order for this to happen with high probability, I can raise this to log n, and after log n rounds, then with high probability, I will not be missed. And all of the nodes will not be missed. And this is, again, why I need the high probability to be at least 1 over n, so that in all nodes, this will actually happen. So a very simple analysis actually shows this powerful result that says that this actually happens. This is a randomized protocol, but with very good, strict guarantees of convergence. So this was the push protocol. I think it's actually remarkably illuminating to also look at the pull protocol. I'll do it kind of quickly. In the pull protocol, I'm using the basic same framework. Every node chooses a partner at random in a round. But now, whenever a node chooses another node to interact with, it pulls information from it. Whatever it has, it pulls from it. What happens in this protocol is that a very, very same analysis to what we just had says that the one, when we start, the one node that actually has the message will be selected by one other node with constant probability, exactly the same probability as in the opposite direction. So that's good. So this will look a little bit like gossip. So one node pulls from the informed node, looks a little bit like the informed node pushes to one other node, except that with non-negligible probability, this will also not happen in the first round, or the second round, or 10 rounds. And in fact, it's not unlikely at all that for logarithmic number of rounds, no pulls will be successful. Only after log n rounds can I guarantee that even a single pull succeeds. And the same thing happens if 1 or 2 pulls succeed and we have a small constant number of informed nodes. We can still, not very unlikely that we'll miss them, or definitely not grow the set of informed nodes by a constant factor. So there's a long startup of the pool process until we reach a logarithmic size of informed set. Once we cross that threshold, then the rest of the first part of the process behaves exactly like push. So the set of informed nodes will increase by a constant factor in every round. The second half of the pool process, once a significant part of the network, half of the network is informed, that's actually considerably different and remarkably insightful to what goes on in the gossip process. So now we have some fraction, let's say half of the network, which are informed, and the other half is uninformed. So let's say that we have some fraction which are uninformed. I'll call that fraction C. So C times n nodes are uninformed. So very, very basic math, really nothing complicated. You can immediately see that an uninformed node stays uninformed with probability C. So we have C times n uninformed nodes. An uninformed node picks a node at random with probability C. It picks an uninformed node. With probability 1 minus C, it picks an informed node. So the expected number of uninformed nodes goes from C times n to C squared times n. But this is very, very different from 2 times C. So now we're squaring the fraction of uninformed nodes in every round. So if we start with half of n uninformed, in one round we grow to a quarter. In the next round we grow to... No. Good. That's what I was ready for. So not to an eighth, but to 1 over 4 squared, which is 16. Great. Not to put you on the spot, this is really takes kind of a moment to stop and think. This is a really much, much faster process. This is not an exponential process. This is super exponential. So again, very trivial math, nothing complicated, sorry. But what it means is that in the pool process now, the part of the gossip process which is heavy, which is really sending a lot of messages, converges much, much more quickly. And if you do the math, it's log n rounds. And log n rounds, to this audience, to me, anybody who's done anything in systems, that's as good as a constant. That's a really, really small number. So pull and push are very, very different. And this led to a beautiful result in the 2000 paper, Fox paper by Karp et al., where they've combined push and pull. They said, well, pull has this long warm-up, startup phase, but then after it reaches a certain fraction of the network, it converges much, much more quickly, much more efficiently, and with much fewer rounds, but not just round messages. If we could only identify when to transition, then we're good. And so they've developed a simple protocol that carries information with it and identifies when to switch over. And so then the first part of gossip, where the first informed node sends to 2 others, then 2 others send to 4, and all of this initial phase, we're only sending linear number of messages. And then in the second half, if we switch to pull, we're sending almost linear. We're sending n times log n, which again is very, very, for all practical purposes, is almost linear. So to wrap up the first protocol in this family, and really the one that started the interest in randomized gossip protocol, the basic rumor mongering, basic information dissemination by gossip protocol. We didn't talk at all about this, but it's inherently fault tolerant. If we choose a random partner that's faulty at any point in the protocol, it's remarkably resilient to that. It's very simple. We talked about it being one line. And when you understand the round and the message complexity, you could see that, first of all, the round complexity is as optimal as it can be. The message complexity, well, there is a cost. Naively, you pay n times log n transmissions. Less naively, you can potentially bring it down to n times log n transmissions. So you pay slightly more than some deterministic multicast regime, but still you gain, amazing simplicity and fault tolerance. At the same time, I also emphasize that all of this works, and we can analyze it in a full network with perfect knowledge of the network. We don't know anything if any process has only partial knowledge, some selection, some random subset of the network to talk to. We don't know anything about the convergence of this protocol. Any questions before we move to interesting use cases? Yes?
All right, I wasn't really clear on this. Is it possible, like when you're doing the push protocol, to make sure a node doesn't push through the same node?
Nope. So this is protocol specific. Oh, sorry. So the question was, is there any way to guarantee that the same node is not picked twice as a gossip target, either by the same node or even from two? I mean, you can patch the protocol. The basic framework did not preclude this and does not need this. So that didn't answer your question. So
I was talking the same node, like so the same node is pushing, it wouldn't push the same node twice.
So you could definitely add to your algorithm some simple test that removes this duplicity. It's not going to change the most of the complexity and the analysis remains exactly the same. But you could definitely avoid this. This is really unnecessary. Not much efficiency is lost there. That's not a common event. Yeah. Okay, yeah?
I was just curious, do you happen to have, for example, a number for some, in an example system where this has been deployed, a number for what the probability actually is after, the O log n number of rounds that we got very unlucky and didn't reach them all? Because it seems like in this, we don't really know if we did or not, so it seems like an interesting number to know.
So these numbers can easily be computed, and they are in the papers. I can't give you a number at the top of my head. It's also not a number. It's a function of n.
Yes.
But I can tell you it goes very quickly. I mean, this is an exponential process, so it goes down very, very quickly, polynomially. If you do 2 log n rounds instead of 1 log n rounds, already the probability grows to 1 over n squared. If you do 3 log n rounds, it will be 1 over n cubed. If n is even 100, that's starting to get really, really low. So you could definitely pinpoint the probability very easily and very precisely. Yeah. Yeah, one more question here, and then maybe I'll continue and defer questions to the end. Yeah.
Yeah. When you switch to the pull protocol, how do the nodes that don't know that they need to know something know that it's time to pull?
Yeah, so that's a perfect question. I'll refer you to the paper because I don't have time to go over it. It's not a trivial protocol. It's a really, really nice protocol. It's also not a complicated one. Really beautiful protocol. I recommend that you read the Fox paper. Now, maybe it will look a little bit more accessible. Fox is a very scary conference in general, but yeah. I don't know. All right. So now let's switch gears and talk about one of the most exciting use cases that I see in practice these days, and that's failure detection. So the work actually started by some early paper on gossip-style failure detectors by Van Renesse et al., which simply used gossip to replace the multicast of heartbeats in a network. That did not actually work too well, and that led to an improved attempt in the SWIM protocol. So the SWIM protocol is what I'm going to talk about today. So in a nutshell, what SWIM does is two components for maintaining failure detection in a scalable network. The first one is to say, we don't want everybody to monitor everybody else. We don't want this quadratic behavior. We also don't want a centralized monitoring service to have to monitor a very large and scalable network. So what we're going to do is we're going to use this randomized regime, randomized framework for monitoring. So in every round, we're going to let each node pick a node at random and test its health. Send it a message and wait for a reply. And because this somewhat ad hoc testing is less stable, less predictable than actually having a heartbeat monitoring service implemented over some reliable transport like TCP/IP. Because of this ad hoc wake up, send a message and expect for a reply, that has some stability concerns. The second idea in SWIM is that when a response does not arrive, we elicit help from peers and ask them to also try to ping a node that's not responsive. We only actually detect or suspect a failure if all of the group of peers jointly do not receive a response from this node. So this is the first part. This is a randomized failure probing or health probing. The second part is, what do we do when a problem is detected or some change is detected? And here, again, the idea is to use gossip to disseminate only these changes alerts, only these rare alerts and notifications. We use gossip for them. So some of the nice ideas and properties that are promised by this paradigm is, okay, we don't have a centralized monitoring service and we don't have all-to-all, but because of the nice properties of gossip, we know that every node has a pretty good chance, has a constant probability of being selected by one other node in a round. Okay, so every node is expected to be selected by one other node and also has a constant probability of actually being selected. So if there is a failure, with constant probability, some node will detect it. So this is, this is a completeness property. And at the same time, because everything is built on top of the gossip framework, the fundamental overhead appears to be constant. In every round, essentially, we're forming a constant number of interactions. So no matter what we do, we send information, we expect responses back, it fundamentally scales. And also, this idea that we separate the monitoring and the actual dissemination of alerts, that's also a really nice property and a really nice idea of this framework. Monitoring is something that you need to do periodically, and there's no way around it, and we use randomization to drive the cost low. Alerts and notification, on the other hand, they should be pretty rare. So we don't want to conflate these two and have to exchange information about the status of the network in each and every round. Only when actually something occurs, then we actually need to send alerts. So this is the basic idea in SWIM. And let's again see the protocol by example. So here's a case where we have a network. For the purposes of SWIM, I needed some more nodes to fill up the slide. We're not going to be able to do it with 8 nodes. And potentially one node, A, here is faulty. So with constant probability, some other node, B, will actually choose it as a random partner. Within a few rounds, this will hopefully happen. We'll send a message, we'll not get a response. So it will elicit help from peers. So now there's a peer group. They're all sending messages to A. All of these messages are not being answered. And then there will be a failure detection. And so this will lead to a normal gossip protocol. So now B wants to gossip to the network information about the failure detection. So it's going to spread around this rumor, A is faulty. And this will work as we've seen before. First, there's only one source. Second round, there are already 2 sources. And, we expect this exponential behavior where nodes are spreading this information, and very quickly, within logarithmic number of rounds, the network knows about it. Okay, but wait. Let's actually go back to the first time that this gossip is sent. At this point, we already know from before, very, very few nodes know about this. At this point, it was the origin, and now it's selecting one more random partner. So the rest of the network doesn't know about the failure, and we're going to take our time and gossip about it slowly. But remember, meanwhile, we're continuing the normal operation of the swim protocol. So in the next round, with good probability, another node will pick A as the target for monitoring. So this is the node C. Node C picked A, doesn't get a response. What is it going to do? It's going to elicit help from peers. So now there's a peer, a group of peers that are all also swarming A with probes. And the same thing happens in the next round. So now 2 nodes are gossiping about A's failure to 4 nodes, but still most of the network doesn't know about it. So there's a node D now, which also probes A. And again, there's a group of peers that come along for the help. And this will actually continue, as we know, until about half of the network already learns about the failure. Everybody in every round will continue probing the same process A, and this will result in an inflation of probes all targeted at A because we're now eliciting peers to help. And so if there's a node that is having any kind of transient network problems or any slowdown, what will happen is that after once it's detected to have a problem, actually the next rounds will only exacerbate it. It doesn't have any steady monitoring relationship with any centralized monitoring. In every round, again and again, a group of messages will actually target it. Also, if there is in fact a failure, if A was faulty, it may take quite a while. So in a large network, people are talking about 1,000 or 10,000 nodes. Order log n rounds to spread this information is quite a while. So we saw that until actually information about the failed response spreads in the network, that could take quite a long time. And remember, we don't want to, this is a failure detection. We don't want to send these probes too frequently. So the gap, the period between rounds is pretty sizable. So it takes quite a long time for this information to actually spread. And during this time, as we saw, all of the probes and the probing will continue. So one might ask, I don't know, and I invite a discussion, and I'll be happy to hear some of the experiences you have, but one might ask whether some alternatives could actually help here. So some of the alternatives is to actually use and leverage the transport protocol, strong properties, whether it's TCP/IP or something else, that actually is pretty good at detecting failures and having stable connections, perhaps along a ring or some other hierarchical structure, perhaps even have a heartbeat monitoring relationship where when a failure is detected, then it's forced on the other side. Who knows? That might actually get over some of these difficulties. But we're not even done. Let's continue looking at the swim process. And now let's look at a slightly different scenario. So here, A was not actually faulty. So either we missed, some response from it, or maybe even A was the one that was faulty. Maybe it, slept for a while, came back, and missed all of the responses that A sent it, and also the peers that it recruited sent it. So there's this faulty notification, which is which we start to gossip. And immediately, another node, in the next round, probes A and actually discovers that A is healthy. So this is the green probing. But it's not going to do anything about it because nobody reported that A is faulty yet. Gossip takes a long time to actually propagate. So this can happen to C and can happen to D. And in fact, again, we know that up until almost the end of the gossip process, most of the network doesn't know about it. Only after a logarithmic number of rounds, when we reach, let's say, half of the network and half of them know that A is faulty, Only then do we expect some node to emerge that both heard that A is being suspected and goes and probes A in that round as the random partner and sees, oh no, A is alive. So here we're starting to see that additional enhancements to the protocol were needed. So SWIM introduced this model where actually when a failure detector, it's not a failure detection, it's just a suspicion. So everybody holds on to it for a while and don't actually remove the node from the membership and see whether there's any conflicting information. If anybody actually probes the node and finds that it's healthy, it's going to start a conflicting rumor. So now we have one rumor about the failure and another conflicting rumor saying the node is alive. And we know that these rumors are completely randomized, so they're arriving at different orders to different nodes. Some of them hear about the health of the node first before they hear about the suspicion, and the other way around. And all of this is going on through a pretty prolonged period of time, because we're talking about a logarithmic process where each probing period is itself non-negligible. And so at some point, we also need to stop this and to say, when do we stop a suspicion? So that's a confirmation, which is, again, a third rumor, where a node decides, OK, a suspicion has been stable for a while. I haven't heard anything new. Now I'm going to confirm this. But now you need to get the rest of the network to converge. So here's a third rumor that confirms this suspicion. So this works great in the case where there was a failed suspicion, a false suspicion by B. So B was out for a while, suspected A, tried to spread a rumor that A was faulty, and then immediately everybody corrects it. This could work great. Except that, wait, what if A really was faulty? But the last message from A actually did reach C. So C has heard that there's a suspicion about A and tried to probe it coincidentally in that round, and was actually able to get some responses due to some timing and ordering problem. Well, what happens now is that everybody in preceding rounds will again and again probe A. And this could be C and D and E and, for a logarithmic number of rounds. Everybody will probe A, will find out that it's faulty, will reinforce the gossip that A is faulty, but that there was this one message, one node that received the last response from A saying, no, A is alive, and it's going to supersede all of them. Okay, because this is gossip, everything arrives out of order. So in summary, if you look at some of the enhancements that needed to make SWIM operate, there are quite a few of them. So we talked about the basic difficulty of asynchronously probing. We don't actually have full trust in this probing mechanism because it's so ad hoc. So we're fixing it by having suspicions instead of detections. And then we have false suspicions with this alive messages. We have confirmations of non-false suspicions with confirmation messages. All of these gossips are continuing in parallel. When there's a single, very clear failure crash, yes, it will be detected. Yes, it will spread in the network quite efficiently. It will take a while, but eventually, with some gap, everything will converge. When there are multiple occurrences in the network, not clear. So some of the additional enhancements that were needed in SWIM because of these behaviors were, okay, so we don't really trust this randomized probing to actually reach all nodes in time. So they've actually switched to deterministic probing. So actually they go round robin. So each node has a round robin regime and not randomized probing to actually make sure that no node is missed. And the gossip itself piggybacks on the probing in order to not create too many connections. So actually the gossip itself is also not randomized. It piggybacks on this deterministic probing. And at the end of all of this, very importantly, what you get is a failure detection. In the paper, it's called a weak membership service. If you look for this, it's a tiny little footnote on the second page, footnote number 2, that says everything from now on has the adjective weak added to it, but we're not going to do it in this paper. So this is what you get at the end of all of these patches. I'm going to stop here because I don't want to turn this into a papers we hate conference. I also hear that some people are actually enhancing SWIM and trying to address some of these difficulties that they're actually experiencing in real deployed systems. So this is what it is. So I think I'm out of time. Where's Lishan? Yep. Should I stop for questions? Because I didn't get to the third.
5 minutes for questions, yeah.
5 minute questions. Okay, I have a third part, but you're going to have to invite me again, to hear about it. That's fine, that's fine. Network discovery, great.
Yeah, we get about 10 minutes. So.
No, you know what? I'm going to flash something about network discovery and leave you to it. So one thing to realize is that all of this was in a full network. What happens in arbitrary graphs? Well, clearly, in some graphs, this process is going to take a long time. So if the graph is a line, it's going to take linear number of steps for a message to get from one side to the other. There may even be graphs where the behavior will be super linear. So this single barbell graph is a classic example where there's one node connected to a dense clique, and it may take n log n rounds until that edge is crossed, until this one node is picked by its single neighbor. So the question is, what can you do in arbitrary networks in general to disseminate information more quickly? And I just want to flash a result. So there's a really, really beautiful paper by the engineers at Akamai from PODC 99, where they introduced the Namedropper algorithm. Allegedly, it was used in some early versions of Akamai. I don't think it's the case anymore, but very, very quickly, just to say what it gives you. Lots of demonstrations. So what Namedropper gives you is that for any graph, even only directed graph. So if you think about the TCP/IP network, if I know somebody's TCP/IP or IP address, that's a directed edge from me to that other node, but it doesn't mean that it's actually symmetrical. It doesn't mean that that other node knows my IP address. So even if the graph is directed, is only connected in a directed way, not completely connected, the Namedropper algorithm will collapse the entire graph into a clique where everybody knows everybody in essentially log squared n rounds. Even less, it's log n times log the diameter of the graph, which of course is at most n. And that result has already been improved somewhat with a deterministic protocol that actually brings it down to log n. So really beautiful and powerful result tells you that even if your network is not a clique, you can talk to everybody at the same time, you can very, very quickly build the network through this gossip protocol, again in essentially logarithmic process. And within this logarithmic time, everybody will know everybody else. And so with this, I will actually conclude and open for questions.
What are the properties of the network that make this applicable or not applicable? Are there cases where you wouldn't want to use gossip? Is it like the latency of the links or the topology, that kind of thing, or the total number of nodes versus bandwidth?
So that's a good question. Probably people here have more experience. From a theoretical point of view, all of this assumed, very basic uniformity. So if there's really huge skews between latencies, between nodes, some of them are really close by, other are, off in the cloud or away. Gossip doesn't seem like a good choice, or at least straight gossip doesn't seem like a good choice because you have to tune these rounds to the slowest link. So gossip is fundamentally, this very uniform process, full knowledge, perfect knowledge, perfect ability to pick a partner, and to succeed in interacting with it. I actually don't know of many cases where gossip in practice gives you a very, very good solution. This is why I wanted to speak about Swim today, because this is one of the very few emerging cases where people use gossip semi-successfully, but still with a lot of problems. We have one here. Hope that answers.
Hello. Thank you. Just have a quick question, and might be basic. At the very beginning, you mentioned that everyone has to know a priori all of the other nodes that are within the network. So I was just wondering, maybe it was covered in the slides and just missed it. How does it affect other nodes leaving and joining the network, or the gossiping, or is it this handled outside of the gossip itself, or what's the difference?
So the question is, if I can rephrase it, how can you use gossip to maintain membership when you need membership to make gossip operate? And I'm asking myself the same question. Yes, the only analysis that we have is when you have full and perfect ability to sample the network. What happens if you have partial sample that's not really uniform? We don't know.
With the Swim protocol on large networks, has it ever been a concern that when you're trying to reconfirm a failure that you're actually going to do like some kind of denial of service against that node and then have a certain ratio of failures that just kind of never goes away?
I haven't seen such a concern. I don't think security was at all a consideration in any of these protocols. I'll take this opportunity to say a comment that may or may not stem from what you're asking. So Byzantine failures or malicious intrusions, these protocols are not built to tolerate. But let me also say, fundamentally, it seems to me that when failures occur, there are essentially two classes of scenarios. One is when there's a single failure, or very few nodes fail, and fail in a kind of black or white way. They crash and that's it. They're not responsive. And the other is when there's some transient partition, half of the network is partitioned away from you, maybe permanently, maybe it is black or white, or maybe there's some transient network failure, or messages are dropped excessively, but not completely. The first type, I think almost any mechanism that you implement will work with. You could do, just a group of monitors, you could do all-to-all, you could do almost anything, and probably also Swim will converge very quickly in that setting. The second type of scenario, that's where the mechanism really is put to a test. And it's not exactly Byzantine, so it's not exactly what you're asking, but it will cause removal of non-faulty nodes and errors and false failure detections and all of that. So I think the effort in tuning a system and engineering it correctly should be on the second case, and that's what should be tested and optimized for. Does that address it all? Yeah, I don't seem to have a good luck with you. I mean, the strict answer is no, I haven't seen any.
I wasn't really getting with the security part, just the protocol itself, where they're being flooded by reconfirmations.
Yeah, so I mean, these confirmations in a non-steady state could cause removal of perfectly okay node. Yes. Sure. Yeah, last question.
I noticed in the example that it was primarily binary, healthy, not healthy. Is there the option of accommodating something more like a nice factor, where it's like, I've had trouble against that particular node 30% of the time? Because in a degrading state, something will often go from full uptime to 50% to 15%. So I'm just wondering if the gossip protocol could accommodate matching that range.
I think gossip just spreads disinformation. What you do with it, I think yes.
Okay.
Or how you interpret it, whichever way you want. All right, thank you very much. Been a great audience.